Learning Outcome 2, Functions and Algebra, 12.2.7. A. Investigate and use instantaneous rate of change of a variable when interpreting models of situations, demonstrating an intuitive understanding of the limit concept in the context of approximating the rate of change or gradient of a function at a point. Establishing derivatives of the following functions from first principles. F of x equals b, f of x equals x, f of x equals x squared, f of x equals x cubed, f of x equals 1 over x, and then generalize to the derivative of f of x equals x to the power n. Use the following rules of differentiation. C. Determine the equations of the tangents to graphs. Welcome back to our series of lessons on calculus. By the end of the last lesson, we had really made some significant progress in solving the problem that we had been working on for a number of lessons. Today we're going to bring it all together and introduce the vocabulary of differential calculus. MacGyver will be helping us again today. Hello MacGyver.
Hi there everyone.
We are not going to go over everything that we have done so far, but I'm going to remind you of the more general description of our mathematical problem which we had devised and to tell you where we are in solving the problem. Our first objective was to find the coordinates of the turning point of a graph. We realized that we will know that when we know where the gradient of the tangent to the graph is 0. And so we developed the more general problem, namely to find the gradient of the tangent to a graph at any point on the graph. By the end of this lesson, you should be able to determine the gradient of the tangent to a function at any point on the function for many different functions. Now, where were we in our problem? Can you remind us, MacGyver?
Absolutely. By the end of the last lesson, we had reached a point where we found the rule for finding the gradient of the tangent to the function y equals x squared and y equals x cubed at any point x, fx on these graphs.
That's right. And we did that both by numerical exploration and by algebra.
This is the table developed for the function fx equals x squared. By simply looking at the table, we could see that the gradient of the tangent at each point on the curve must be twice the x value of that point.
Hold on there a second, please, MacGyver. I want to introduce a name for what we have found. In calculus, we call that the derivative. MacGyver, can you change that on your table for us?
Okay.
You can change it to the value of the derivative. I know that it seems like a lot of words still, but I want you to use that long phrase now so that we really have a clear understanding of what we are finding. From now on, we will use the proper word, the derivative.
Derivative? That's a strange word. Where does it come from?
Well, it comes from the word derive, which means to obtain from something. For example, we might say that we derive pleasure from dancing when we mean that we obtain or get pleasure from dancing. In our situation, we get the derivative of a function from the original function. If we go back to the table, here, we wrote the values of the gradient of the tangent for each of the x values. From that, we made this observation about a more general rule for determining these values. The process by which we determined these values is called differentiation, and this general rule is called the derivative. So, the general process we used here, called differentiation, helped us to determine the derivative without having to consider the values of x one by one. The derivative, denoted as f dashed or f prime of x, is the gradient of the curve f of x and also the gradient of the tangent to the function f of x at the point x, f of x. If you think how hard we worked with the original function to determine it, I like the word derivative. It really gives a sense of how we obtain the new function from the old function.
Through hard work.
Exactly. Let's quickly look at the other derivative we determined. In this case, the function is f of x equals x cubed. And the gradient of the line between x, f of x, and x plus h, f of x plus h, is 3x squared plus 3xh plus h squared. When h is very small, this gets very close to 3x squared, which is the derivative. Now, MacGyver, do you remember where our whole journey of discovery started?
If I remember correctly, we started this whole journey because we wanted to find the maximum volume of a box made from a 20 centimeter by 20 centimeter square piece of cardboard. Are we finally ready to answer this question?
Almost. But first we need to introduce a little more notation.
Okay, let's do it.
To start with, what we call the gradient here is the gradient of the straight line between the point x, f of x, and x plus h, f of x plus h. The curve changes all the time between these 2 points, so we are using the gradient of the straight line between these 2 points to give an idea of what's going on with the gradient of the curve. Because of this, we call that gradient of the straight line between the points x, f of x, and x plus h, f of x plus h, the average gradient of the curve between those points.
And the derivative?
Let me write that up here. The derivative, which we denote with f dashed of x, is equal to the limit as h tends to 0 of the fraction f of x plus h minus f of x all divided by h.
Is that similar to the gradient? Oh, sorry, average gradient. Except you've written this funny limit thingy.
Quite right. Although the funny limit thingy will make sense in a few minutes. Now I can do all the same algebra that I did earlier using this formula.
Okay, so now we have that f dashed of x equals the limit as h tends to 0 of 2x plus h.
Right, and before I write more, can you remember what happened in those tables and on the computer as we brought the points closer and closer together?
Yes, I can. As we brought the points for the function fx equals x squared closer and closer together. So the value of what we call the approximate gradient got closer and closer to 2 times the x value of the point of interest on the function.
And that is all we mean by what you call the funny limit thingy. When we say the limit as h tends to 0 of 2x plus h, we mean what happens to 2x plus h as h gets smaller and smaller and smaller and smaller and...
Why are you going on saying smaller and smaller? If we are making h so incredibly small, why don't we just make it 0 and cross it out?
Because if we made h 0, we would have 2 points that have no distance between them. And in terms of our gradient equation, that would be like dividing by 0, which is a problem because division by 0 is undefined.
Oh, I get it. So it would be like finding a gradient of a line using 1 point, which is impossible. The problem that got mathematicians going all those years ago, and which we have been busy with for several lessons now.
Absolutely. But I was going on and on like that to make it clear to you that we can make h just as small as we like.
So small that even with zooming, we will hardly notice it on the graph.
Quite right. And as h becomes smaller and smaller, so this expression will get closer and closer to just 2x, which we write as just 2x, and 2x is the derivative of x squared.
I see your point, but it looks like a lot of fussing, doesn't it?
It is a lot of fussing, but this represents one of the greatest breakthroughs in mathematics, and it was invented as recently as 320 years ago.
Recently? 320 years is a very long time.
But if you think of it in terms of the history of maths, it's a short time.
I suppose so. So are we ready to finish the box problem now?
Nearly. First, let's look at the other functions we were working with. The function f of x equals x cubed. I have jumped ahead and I've already made the changes.
Yes, I see you've added the word average. You have also derived the derivative f dashed of x. But I see that you haven't gotten rid of the limit thing yet.
I wanted to talk about that last step with you. What it says right now is the derivative will be the limits as h tends to 0 of the expression 3x squared plus 3xh plus h squared. What will happen as h gets very small? In other words, very close to 0.
But not 0.
Right.
Well, h squared will get very, very small. Much smaller than h itself. Since squaring a fraction results in an even smaller fraction. So as h gets smaller and smaller, h squared will also get closer and closer to 0.
Good job. And what about 3xh?
As h gets smaller and smaller, so will 3xh. And so we can say that as h gets closer to 0, so will 3xh.
Wonderful. And that is why we say that the derivative is equal to 3x squared. In our school curriculum and in exam questions, we call this whole derivative process determining the derivative from first principles.
I've heard that expression before, but I didn't know what it meant. But tell me something. Does this mean I have to use this whole process to determine the derivative when they say using first principles?
It sure does. But luckily there is a pattern in all of this, and using that pattern we will be able to find derivatives without the long process. In other words, there's a short method that you can use in the cases where you aren't specifically asked to derive from the first principles.
Really? That's good to know. Can you show it to me?
Of course. Let me take this fresh page and make a summary of what we have done so far. We have two things, a function and that function's derivative. So far we have shown that if the function is f of x equals x squared, then the derivative is f dashed of x equals 2x. And when the function is f of x equals x cubed, then the derivative is f dashed of x equals 3x squared. And in the task for the previous lesson, we showed that when the function is f of x equals x, then the derivative f dashed of x equals 1, and when f of x equals a, where a is a constant, then the derivative is f dashed of x equals 0. Is there enough for you to work with to guess the derivative of f of x equals x to the power 4?
It seems that with the others,
That the exponent of the term in the original function became the coefficient of the term in the derivative.
so would it be 4 times x something?
Good job. Now, what about the exponent?
Well, with the function x cubed, the derivative had an exponent of 2. With x squared, the derivative had an exponent of 1. Although, of course, we don't write that. And with just x, the derivative had no x, which could be thought of as x to the power of 0, 1 less each time.
Will this one's exponent be 3?
It sure is. We can generalize what you have just observed to say that when the function is x to the power n, then the derivative is n times x to the power n minus 1. We call this the general derivative.
And that was discovered 320 years ago.
You're quite right. Years ago, Leibniz and Newton each discovered this rule, and it has allowed mathematicians to solve problems which they could not solve up until then. 2 more derivatives and you're ready to finish the box problem. How about the derivative of the function f of x equals 4x squared?
Well, the derivative of the x squared part is surely still 2x. But what about the 4?
You may not realize it, but actually we can simply say that the derivative is 4 times the derivative of x squared. 4 times 2x, which is 8x. In other words, the derivative of any constant a times x to the power n equals a times n times x to the power n minus 1.
That is not too bad. But what about something like fx equals x cubed plus x squared?
Well, to help us with that, we have a little rule that says that the derivative of the sum of functions is equal to the sum of the derivatives of the functions.
If I understand that correctly, then the derivative of the function x cubed plus the function x squared is equal to the derivative of x cubed plus the derivative of x squared, which would be 3x squared plus 2x.
Well done. Now that is really great work. And now we can finish off that box problem.
Finally.
Earlier we established that the volume of the box could be determined using this formula here. We used a computer program to draw the graph of that function, and this is what we got. We made the point that the part that I have highlighted in green is of interest to us for the box, although the graph of the function extends well beyond that. Because we wanted to know what the maximum volume of the box is, we wanted to find the coordinates of the turning point. The x value would give us the amount that we must cut out, and the y value, the maximum volume. And we decided that the maximum value would occur where the tangent has a gradient of 0.
And that got us searching for a way of determining the gradient of the tangent to the function at any point of the function, which we now call the derivative, right?
Right. Let me write the volume as v of x. Since the volume is a function of x, the amount that we cut out, and we know that to be equal to. Now we will have to multiply out the brackets if we want to use the methods we wrote down earlier. So that gives
400 minus 80x plus 4x squared, all multiplied by x. Then we multiply the brackets by the x. If we simplify that, we get 4x cubed minus 80x squared plus 400x.
I want to differentiate this. So I'll write v dashed of x equal 4 times the exponent, which is 3, times x to the power 3, minus 1, which is 2, minus the 80 here, multiplied by the exponent, which is 2 times x to the power 2 minus 1, which is just x plus 400, times 1 times x to the power 1 minus 1, which is x to the 0, making the last term of the derivative just 400. which can be tidied up to give 12x squared minus 160x plus 400.
Cool. What's next?
Well, we have been saying that the gradient of the tangent at the turning point is 0. So let me write that here. This gives a quadratic equal to 0, which I must solve. And that says that either x must be 10 divided by 3 or 10, two turning points. You still with me?
Yeah.
Looking at the graphs that suggest that there is a turning point at 10, but it's not the one we're interested in. The other turning point is x equals 10 divided by 3. A little more than 3, and here it is. Yes, we found that when we cut out a square 3 and 1/3 centimeter, then the volume of the box will be a maximum.
That's so cool. So if we make the side 3 and 1/3 centimeter, we'll get the biggest possible box.
That's right. And I think we'll leave it there for this lesson. Time to recap on what we have learned today. As a task from the last lesson, we calculated the gradient of the line between any point x, f at x, and the point x plus h, f at x plus h on various curves. Most of these curves were familiar. The straight line parallel to the x-axis, f of x equals 1, the straight line through the origin, f of x equals x, the parabola, f of x equals x squared, and an unfamiliar one, f of x equals x cubed. We realized this was the average gradient between the 2 points for any value of h. When h is negative, the point x plus h, f at x plus h, will lie to the left of x, f at x, and for h positive, the point will lie to the right of x, f at x. We then define differentiation as deriving the limit of the average gradient f at x plus h minus f at x all over h as h tended to 0. From the table of some powers of x and their derivatives, we made the generalization that if the function is x to the power n, then its derivative is n times x to the power n minus 1. We also accepted the following three rules. If one function is a constant a times another function, then its derivative is a times the derivative of that function. If a function of h of x is the sum of f of x and g of x, then its derivative is the sum of the derivatives of f and g. And if a function h of x is the difference between f of x and g of x, then its derivative is the difference between the derivatives of f and g. Once we had developed some confidence in differentiating simple functions, we returned to our original problem of finding the length of the square that needs to be cut from each corner of a 20 centimeter by 20 centimeter piece of cardboard to make a rectangular box with the greatest possible value. We realized that the maximum volume would occur when the derivative of the volume function was equal to 0. We differentiated, put the result equal to 0, and solved the resulting equation. At last, we were able to confirm that, as expected, the cut-out piece was a little more than 3 centimeters. In fact, it must be 3 1/3 centimeters to produce the biggest possible box. The other root of 10 was not applicable because the domain for which our volume equation makes sense is between 0 and 10. And the volume for a cutout of 10 centimeters is 0. The box disappears altogether. I think that you need to spend some time reflecting on what we did today. And therefore, your task is the following. I'm going to ask you to repeat the work that MacGyver did in the last few minutes, but also to calculate the actual maximum volume. I think we're making great progress in our journey of discovery of calculus. Join us again next time.